So I will start. So my name is João Correia, and I'm here to present this talk about evolutionary computation in a control bridge design solution with deceptive landscape. Okay, so what is the problem that we are trying to solve, or the challenge? We're trying to design cable state bridges, okay, something like this in this picture, and we obviously want to minimize costs, but we want to build them with some structural constraints that must be attended. Okay, we have access for some normalized decision variables regarding the constructions of this type of bridges. And basically, what we try to do here is to apply evolutionary computation to this problem, taking into account that there are some optimization techniques in place from the state of the art, but many of them do not use as much decision variables at one time, and it's an interactive, iterative process where a human has to be in the loop to control and project how this bridge will come to life. Because this is really important, because of course we don't want this to happen. This is the Tacoma Bridge. I'm sorry about the bad quality image, but this is quite old. But basically, in this type of bridges, we can come up with a solution that we, on paper, think it's okay, but then when we put it and built it, we can have various problems. And this one was famous because engineers at the time told that it was perfect, calculations were right, but they forgot that sun, temperature, wind could affect the materials and make it to swab around until it collapsed some years later. So this basically where we are trying to apply EC to this problem to check if we can optimize the parameters to give us a bridge that won't collapse in the future. Okay. So what are our constraints? Because we want to explore a different type of variables to make this happen, but we have some constraints for this setup. So we have a constraint of number of towers that we are going to use. In this case, we are using two towers, and we are trying to project a bridge for 220 meters. Well, this is a bit of on the civil engineering side, but we use 4 cables to connect all the bridges. And based on literature, the best solution, taking into account some prices around the cost of materials and to execute this build, we are talking about 9134 K euros, so 1,000 euros, and a maximum constraint value that was obtained for this optimization problem, it's around 0.9. I will talk a little about this value. We want some constraints, some physical constraints and structural constraints to be under or around a certain value because of certain Euro code regulations. And so basically what we're trying to do is maintaining this max structural constraint lower or around 1, the value of 1, and we want to minimize the costs of our bridge at the same time. We have access to 20 normalized decision variables that affect the design of the bridge, such as in bridge length, dimension constraints, tower lengths and constraints, and structural response devices constraints. So the structural devices will also help the bridge to become more stable, and we are trying to adjust the position and the size of these devices. Well, basically, with this challenge, we throw a typical conventional, straightforward genetic algorithm to do this. And we try to do this with, well, a representation of the individuals being the decision variables, values for those decision variables, a pretty standard crossover. Mutation will replace one of the numbers of these of the individuals, and we use tournament selection to select the best designs, bridge designs to the next generation. For fitness, since we have this, well, two constraints or two objectives in mind, we tried a simple approach where we basically want to minimize one part first, and then we try to minimize the other half. And so here we have the cost of an individual being C of X, and the structural, maximum structural value of an individual being S of X. Okay, we define some constant target variables to try to guide our algorithm to this, well, to come up with an optimal solution. And we try to do this in three phases. So one phase was just throwing out the algorithm and try to make some generations with 50 individuals. These are some of the parameters. You can check more on the paper. And we basically, with our first experiment, we tried this and we got something like this. And we were a bit, this is going to be harder than we thought. Okay, so basically we prematurely stabilize on a value that meets the constraint of max of structural constraint, but then minimizing the costs is not an easy task when we get there. And so we can see that the average population is here up and down, and we have the maximum almost stagnant just in the couple of first generations. We now we checked also the other values, so the S of X, the best structural constraint, and the best of the cost. We can see that we have, this is logarithmic scale, and we have, well, even though we have a good solution that is, well, the best solution is really under the one value for structural constraint, but it costs in the orders of millions of euros. And of course, we want to avoid that. And we can see that then it tends to become lower. And even if we basically do a close-up of the cost after 400 generations, we can see that we can gradually come to a value that is still far from the baseline, okay? But, well, we can evolve solutions that go towards a lower price and meet the constraint demands. Then we tried something different. We tried to do some local search by including the optimized solution, the baseline optimized solution in the population since the start. And we tried to run the same experiment. Basically, well, we maintain everything else, okay? And once again, we were caught by surprise, or well, we thought we could improve further the solution that we have, and we can see that there are some alterations. We can still come below the structural constraints, but the value, the cost of the value doesn't change much. It has a slightly better value, but is not really significant. Well, it's not a really groundbreaking significant improve. But then we try to be a little more aggressive with the evolutionary part to try to create more selective pressure, and eventually, without the baseline in the population, we arrived at some better solutions in the experiment 3, but at the cost of a bit of the structural constraint value being a little above the recommended value. But we were able to reach out for the 92 value. More detailed values are in the paper. Here is just an overview for this talk. But basically, with this third experiment, we arrive at similar and better cost-effective solutions. Visually speaking, because it's not all about the numbers, what we are seeing here is the baseline, which is pictured in blue, and we have the solution, the best solution from experiment 1 here represented. So this would be how the ridge would look like in a 2D graphic and minimized version, of course. And we can see they are pretty different, and but well, it took into account the structural constraints, but it costs a little bit more because it uses more points of contact than the best baseline solution. And so it's a bit different, but it still costs us a bit more. And in the third, we can see that it's almost an overlap from the baseline, but with some minor adjustments on the position of the cables that provide a little bit less structural constraint value, but it allows to minimize some costs because the length of the cables are not so long, and so you spare some material, and so the cost goes a little bit down. What does this all mean? What is the impact of this? Basically, we can see that in general, with these approaches, we all came to the conclusion that we could avoid something that happened even with a famous tower, a famous bridge, that is the Millennium Bridge of London. When people were traversing the bridge came to swabble a bit. Not that, well, at the time it didn't happen a collapse or something like that, but basically the swabble is not a good thing to happen. And here in this graph, we can see if with the frequency of pedestrians, how would oscillate the solutions that we found. And we see that we are pretty safe to travel any of the bridges that we came up across during the experiments. Well, the best ones at least. Okay, I'm not here depicting all, but the best ones are safe. So, of course, this is the bright side of this experiment. So we try. The hypothesis was to use evolutionary computation to try and find solutions. I think we got that. Different than the baseline solutions, but we felt that the solution space is really dynamic and deceptive in the way that a small change can leap it through a complete destroyed solution, or a small adjustment can have a ripple effect in all of the design of the structure. So we are concerned now in exploring better the solution space. We want to try also other operators. We want to include more decision variables, and eventually propose this problem as a benchmark problem, since we felt like there are some characteristics from this problem that could be interesting to explore with several techniques from evolutionary computation. And well, that concludes my presentation. Thank you all.